Hello everybody, this is Dr. Abdelkader Ashur. Today we are going to continue our series of videos about neuropharmacology. Previously we gave an introduction about neuropharmacology and receptor pharmacology. Today we are going to talk about the first branch of the autonomic nervous system, which is the parasympathetic nervous system. But from the pharmacological point of view, we are going to talk about parasympathomimetic or cholinergic drugs. Okay, where we will discuss the responses to parasympathetic activation. We try to understand acetylcholine synthesis, release, degradation, interaction with pre and post synaptic receptors, and talk about the difference between true and false cholinesterases, and then finally explain the parasympathetic organ synapse. So to clear some confusion that I noticed from some of your questions about the differences between the parasympathetic and sympathetic nervous system with regard to anatomy. Okay, so I'll just review it quickly here. So regarding the site of origin, sympathetic nervous system originates from thoracolumbar, as we mentioned before, and parasympathetic nervous system originates from craniosacral. Okay. The length of fibers, this was part of the confusion. The sympathetic nervous system has a short preganglionic neuron, short, so the ganglion is lateral, or pretty close to the nervous system, CNS, okay? Whereas the postganglionic is long. So that's because the sympathetic nervous system has what's called sympathetic chain ganglia next to or close to the central nervous system. Okay, that's why the preganglionic is short. And the parasympathetic nervous system, the preganglionic is long. Okay, whereas the postganglionic is short. So the ganglia is called terminal. Okay, so it's very far from the CNS. It's even maybe embedded in the effector organ. It's pretty close to the effector organ or even embedded in the effector organ. Okay, so we already mentioned that the location of ganglia close to the spinal cord in the sympathetic nervous system, whereas in the parasympathetic nervous system it's within or near the effector organ. Distribution is wide, okay, almost everywhere. Parasympathetic is limited, as we'll see in our next lecture. Type of response is diffuse, okay, is diffused. That's why here you have this sympathetic chain ganglia. Okay, there is some communication between these ganglia, so that I make sure the response is the sympathetic nervous system respond as a one unit. Okay, as we mentioned earlier. Okay, whereas the response of the parasympathetic nervous system is discrete. It's just I need like narrowing of the eye pupil, lacrimal secretion, GIT secretion. Each response it's just one single response, discrete. It's not universal. As we said, if this happens, it's going to be a disaster. Please review the previous lecture about that. This is here highlighted here. If you look here, this is the parasympathetic. Look at the ganglia. It's far from the nervous system, so the CNS. Okay, close to the effector organ. Look at the sympathetic. The ganglia is lateral or close to the CNS. So ganglia in the parasympathetic close to the effector organ. And the sympathetic is close to the CNS. Okay, so the response of parasympathetic nervous system activation could be easily remembered if you remember these two words, rest and digest. Rest and digest, very important key. So whenever I am in a state of rest, or I'm eating, or I'm digesting, or whatever, the parasympathetic nervous system should be the predominant system. Okay. So there is a rest, okay. Do I have to have wide eye pupil, like mydriasis, and the see far vision, whatever? No, okay. I'm just resting, okay, for God's sake. So for the eye accommodate for near vision, that's it. And also meiosis, okay, narrowing of the eye pupil. When it comes to, let me take first the heart and the bronchi. Okay, so I'd like to start with the heart. The heart rate will decrease. I don't need to push the accelerator of the car while I'm just stopping in the traffic signal, right? Or the light signal. I'm just stop. Okay, the car stop. You don't like to push the accelerator. Okay, blood pressure will decrease. Okay, the contractility, as we'll see later, and the atria will decrease. But ventricle, there is no action or effect of the parasympathetic nervous system on the ventricles. Okay, the heart rate decreases. Okay, so now the bronchi, sorry, there will be bronchoconstriction. There is no need to have this deep breathing. Okay, because the heart rate is slow. Okay, and the secretion will increase. Just as a key for parasympathetic nervous system, whenever I hear any gland or any secretion will increase. Okay, any secretion will increase if it's affected by the parasympathetic nervous system, it will increase. So here, okay, come here, the salivary secretion increase, copious, large amount, and it's watery. The GI tract secretion will increase. Okay, peristaltic movement will increase. Okay, the motility will increase, and sphincter tone will decrease. This will lead to efficient digestion. The digestion will be very efficient because the GI secretions will increase. Okay, it contains the enzymes and everything, HCl and so many factors that aids in digestion, and the walls of the GIT constrict and the sphincter dilates. Okay, so if you go down at the end of we're going to talk about the anal sphincter or even on the urinary bladder. Okay, the last part, usually the wall contracts and the sphincter relax, so there will be defecation and urination. Okay, I hope this is clear. We leave this guy enjoy his nasi ayam in Malay language, or chicken, okay, in English. Okay. With regard to anatomy, we said it's craniosacral, okay, 3, 7, 9, 10 cranial nerves, and the second, third, fourth spinal cord roots or cranial, segments. So it originates from the CNS through the cranial nerve number 3, which is locomotor, 7 facial, 9 glossopharyngeal, 10 vagus nerve, and the middle 3 sacral segments. Okay, 3 innervates the eye, 7 innervates submaxillary and sublingual glands, 9 innervates pupillary constrictor pupillae muscle and ciliary muscles, salivary and lacrimal glands, mucous glands of the nose, mouth, and pharynx. Vagus nerve is widespread, okay, the most widespread cranial nerve in the parasympathetic nervous system, supplies heart, lung, GIT, and etc. Okay, and even enteric nervous system. Sacral segments 2, 3, 4, they are below. They are very pretty low, right? The last part of the vertebral column, right? So they also deal with lower, okay, body parts like lower GIT, urinary bladder, rectum, and sexual organs. Okay, I hope this is clear. So now let's talk about cholinergic transmission. If you remember in the introduction to neuropharmacology, we talked about the conduction, which is above here, okay, and the transmission, okay, which will occur here, okay, which is manifested by the release of the neurotransmitter into the synapse and binding to the receptor, right? So this starts with the synthesis of acetylcholine. So let's first discuss the synthesis of acetylcholine. So the terminals of cholinergic neurons contain large number of small membrane-bound vesicles containing acetylcholine. These vesicles concentrating near the synaptic portion of the cell membrane. They don't need to be up here. They are present in huge amounts, okay, where they are critically needed, right? So each vesicle contains tens of thousands of molecules of acetylcholine, but where it is urgently needed, which is here, okay, near the synaptic portion of the cell membrane. So acetylcholine is synthesized in the cytoplasm from acetyl-CoA coming from the mitochondria and choline coming from the extracellular fluid, okay, by the action of the enzyme choline acetyltransferase chat. It's not your chat on the WhatsApp or Facebook. It is another type of chat. Okay, choline acetyltransferase, very important enzyme. Okay, that catalyze the synthesis of acetylcholine from acetyl-CoA and choline. Acetyl-CoA, acetylcholine. This will form acetylcholine. This acetyl-CoA comes from the mitochondria. These mitochondria, because I need it in large amount here, so they are present large amount in the nerve ending. Okay. And choline, we are talking about now the precursors. Okay, I need the building materials. Okay, I need choline and I need acetyl-CoA. Acetyl-CoA from mitochondria. Choline will come from the extracellular fluid. But choline, this choline, please remember this word is quaternary ammonium compound. It has positive charge. It has a positive charge. So it's hydrophilic, which means it's lipophobic. Cell membrane is lipophilic, right? Anything that's lipophobic or charged cannot pass unless there is a transporter. The transporter here, okay, is called carrier A, okay? Carrier A, okay, or called simply choline carrier, okay. So choline is transported from the extracellular fluid into the neuronal terminal by sodium-dependent membrane carrier, carrier A, okay. So this choline transporter transport choline, okay, in what they call it co-transporter fashion. So this is co-transporter. You know, transporter, there is a uniporter that only passes one compound from one side of the cell to another. But if there are two molecules or two compounds need to pass, they could pass in the same direction. So it's called co-transporter right here, okay, in the same direction. Choline with sodium. Here we'll talk about the antiporter, but in the next slide. So again, choline will enter into the cell. So now I have the precursor molecules, choline from the extracellular fluid and acetyl-CoA under the influence of the enzyme chat, choline acetyltransferase, acetylcholine is formed. Then this acetylcholine need to be stored in the vesicle. But before that, okay, this choline transporter or carrier A, okay, is could be pharmacologically inhibited by a group of drugs called hemicoliniums. Hemicoliniums, okay, blocked by drugs called hemicoliniums. Okay, so then acetylcholine need to be stored in the synaptic vesicles to protect it from degradation. Okay, so acetylcholine, again, acetylcholine itself is a charged molecule. It's hydrophilic, it's lipophobic. It cannot pass by itself across the lipophilic cell membrane. So it needs another transporter, okay, which is here called acetylcholine transporter, okay. The first one was choline transporter or choline carrier or carrier A. This one is carrier B or acetylcholine transporter, okay. Carrier B because, you know, the steps starts from here. So this is A followed by B. Choline carrier because this one carries choline. Acetylcholine carrier because it carries acetylcholine. Carries from acetylcholine from the cytoplasm into the inside of the synaptic vesicle and stored along with ATP. Remember the co-transporter, so ATP is a co-transporter stored in the same vesicle with acetylcholine. Okay, okay, that transporter, this carrier B, okay, can be blocked by the drug called Vesicular. So Vesicular, okay, as a simple mnemonic, okay, vesicle, okay, and acetylcholine, okay, so inhibits the storage of acetylcholine into or in the synaptic vesicles. Drug is called Vesicular. It's considered as cholinergic physiological antagonist. Okay, release of acetylcholine is dependent. Now I have so much of acetylcholine right here in the vesicle and have so many vesicles here. Okay, so now I need this acetylcholine to be released, okay, to elicit the response or to cause the transmission. Okay, the release is dependent on extracellular calcium and occur when action potential. To remember, conduction is up here. Okay, action potential, action potential, action potential, sodium influx, and calcium influx. Okay. Calcium, along with other special proteins called VAMs, vesicle associated membrane proteins, okay, they facilitate the fusion of the vesicular membrane, this vesicle membrane, okay, with the terminal membrane. This is the terminal membrane, okay. So this results in exocytosis of acetylcholine into the synaptic cleft. So now acetylcholine finally is here outside, okay. So this acetylcholine, okay, can easily after that bind to the receptors, okay. But again, what inhibit this process and what facilitate this process? It's inhibited by botulinum toxin, which is one of the most toxic proteins that have ever been found. It's neurotoxic protein, and this release process is induced by black widow spider venom or toxin, which is also called laterotoxin. Okay, black widow spider venom or toxin or laterotoxin facilitate the release, and botulinum toxin inhibits the release of acetylcholine from the synaptic vesicles into the synapse. Okay. So after release, okay, acetylcholine now can activate or inhibit, can bind to the receptors, activate, inhibit, whatever, okay. So it can bind to the receptor easily and elicit a certain response. But because I need this response to be very discreet, okay, and very elaborate and just to the point, okay. I don't need acetylcholine to continue doing its effect, like what I gave example before. If it's just on the heart, I need the heart rate to go down a little bit, or the heart rate decrease a little bit from maybe 70 or from 80 to 70, okay. I don't like acetylcholine to continue to decrease heart rate until 50, 40, 30. This does not happen. Why? Because there is acetylcholine esterase, okay, enzyme, okay, which can degrade acetylcholine back into choline and acetate. And none of these, choline does not have any significant effect, transmitter effect, or acetate, okay. Thereby, this terminates the action of the acetylcholine. Most cholinergic synapses, okay, so this is the acetylcholinesterase, okay, are rich in acetylcholinesterase. That's why the half-life of acetylcholine in the synapse is very short, okay. So acetylcholinesterase is also found in RBCs. There is another enzyme that can degrade acetylcholine, but less efficiently and less specifically. It's called pseudocholinesterase or butyrylcholinesterase, okay. This is found in blood, the plasma, liver, glia, and many other tissues. Okay. Now we'll see the differences between these two enzymes. So the major differences between these two enzymes, acetylcholinesterase, also called true cholinesterase, or butyrylcholinesterase, also called false or pseudocholinesterase. With regard to distribution, as we mentioned, acetylcholinesterase is available in all cholinergic sites. Okay, to split acetylcholine into choline and acetate in RBCs and the gray matter also. Butyrylcholinesterase is available in plasma, is present in plasma, liver, intestine, and white matter. Regarding the drugs and their hydrolysis by these two enzymes, acetylcholine, the main neurotransmitter in the parasympathetic nervous system, and if you remember also in the sympathetic nervous system, in the preganglionic neuron, it's released from preganglionic and act on nicotinic receptors on the postganglionic neuron everywhere. So acetylcholine is split or hydrolyzed by acetylcholinesterase very fast, okay, in microseconds. But by butyrylcholinesterase, the hydrolysis will be slow. However, methacholine is slower than acetylcholine and is not hydrolyzed by butyrylcholinesterase. Benzylcholine and butyrylcholine. Butyrylcholine is hydrolyzed by butyrylcholinesterase, but not by acetylcholinesterase. Regarding the drugs that inhibit these two enzymes, the acetylcholinesterase is more sensitive to physostigmine. Physostigmine is reversible cholinesterase inhibitor. Reversible cholinesterase inhibitor, or also called reversible anti-cholinesterase. So acetylcholinesterase is more sensitive to physostigmine. Butyryl cholinesterase is more sensitive to organophosphates. Organophosphates are insecticides, and they are irreversible cholinesterase inhibitors, or they call them irreversible anti-cholinesterases. Okay, regarding the function of these two enzymes, function of the acetylcholinesterase enzyme, all the way, it's mainly for termination of acetylcholine action. We said I don't like the response elicited by acetylcholine to continue forever. We need to stop it. Okay, so termination of acetylcholine action. However, butyryl cholinesterase is less specific. It can hydrolyze acetylcholine, okay, slowly, but can also hydrolyze any ester because it's esterase, right? It can hydrolyze even aspirin, acetyl salicylic acid ester, okay, and many other ester drugs. Okay, so it causes hydrolysis of ingested ester, any esters, okay. Okay, finally, we end up with the parasympathetic ganglionic synapse. Okay, now we'll go a little bit in details, okay, of what happens in the ganglionic synapse in the parasympathetic nervous system. First, I'm coming here, so on the left-hand side, there should be what? There should be the CNS, right? Brain and spinal cord. Here, okay, cranial nerve 3, 7, 9, and 10, and sacral segments middle 2, 3, 4, so anyway, so this is the pre-ganglionic neuron. Is it long or short? Long, yes. Okay, so it's long. Okay, pre-ganglionic neuron. Okay, so now I imagine that there is the CNS here, and the impulse or the action potential is coming here. So action potential. Okay, so action potential is coming. Okay, sodium influx, calcium influx, in addition to VAMPs, we just talked about them, vesicle associated membrane proteins. This will facilitate the fusion of acetylcholine containing vesicles, these vesicles, okay, fusion of the membrane of these vesicles with the membrane of the nerve terminal, and then expulsion or exocytosis of acetylcholine. Now I have acetylcholine say, hey, yeah, I'm free now, I can do whatever. Go ahead, okay, but not whatever, okay. There is acetylcholine waiting for you to split you back into acetate and choline. So acetylcholine, okay, with regard to the function, okay, it binds to nicotinic receptors on the surface of the post-ganglionic neuron. Nicotinic receptors are which kind of receptors? We mentioned before there are 4 receptors, right? Ligand gate and channels, G protein coupled receptors, kinase linked receptors, and nuclear receptors, right? We mentioned in details 2 of them, ligand gate and channel and G protein coupled receptor. Which type? The nicotinic receptors. It is, yes, ligand gated ion channels. Please review the lecture of the receptor pharmacology. Okay, so acetylcholine when binds to this nicotinic receptor is ligand gate ion channel. When this ligand, its beloved ligand, binds to it, it will open. Okay, when it opens, allow the influx of sodium. The influx of sodium into the post-ganglionic neuron. This is the beginning of the post-ganglionic neuron. Okay, then please remember, just put it like the next slide, continuum of this slide. Okay, so this is coming in. So the previous slide is here. Okay, so this sodium in the previous slide, sodium here influx, right? Sodium when it enters, it will elicit action potential. So action potential from that sodium, okay, sodium potassium action potential, positive negative action potential, again sodium calcium influx, and fusion of the vesicles with the nerve terminal membrane and expulsion of acetylcholine. Acetylcholine here will bind to the effector organ. Okay, the effector organ has muscarinic receptor. Muscarinic receptors are, yes, are G protein coupled receptors. G protein coupled receptors, okay, as we say, GI, GS, okay, and G protein associated channels which can modulate the passage of ions through the cell. Okay, this has been discussed in detail in the receptor pharmacology lecture. Okay, so now it can elicit a response. This muscarinic receptor could be M2 on the heart, that this will result in slowing heart rate and decrease atrial contractility and conduction velocity. If it's on the eye, it will cause meiosis. If it's on the GIT, increase secretion, increase motility, decrease sphincter tone, and so forth. Okay, I hope you enjoyed this lecture, and I will see you soon to continue our talk about the parasympathetic nervous system pharmacology. Until then, I wish you the best of the best and see you later. Bye.